we finally got to a very interesting problem. We have a word problem, and the word problems, we've done several on the homework. Most of them fell into the category of either optimization or related rates. So let's see what this is. A telemarketing company wants to construct new cubicles for their employees. Each cubicle will be rectangular with 3 walled sides, and the 4th side open to the hallway. No wall needed. There is 18 feet of wall material for each cubicle. The company needs your help to find the dimensions that enclose a maximum area. So as soon as you see a maximum or a minimum, you should think a couple of things. Well, I guess I should be underlining the maximum. Maximum or minimum should make you think of optimization. This is a technique that we learned, and I can't remember what chapter it was, either chapter 5 or chapter 6. Optimization, which also means we're going to be using the first derivative of something, because the first derivative will allow us to find maximums or minimums. Remember, the second derivative allows you to find concavity. Okay, so the problem might be stated slightly differently online, but I have broken this up for my in-class students into 2 parts. And the first part is to draw a picture. So draw a picture of the cubicle and label each side with an appropriate variable. Well, my cubicle is going to look like this. It's got 3 walls, right? And the 4th side, there is no wall because there's a hallway. So you don't have to draw it like this, but I like to say, okay, here's my hallway. So there's no wall there. What are the variables going to be? Well, I'm trying to find dimensions. So I can call this x, this y, and this x. Okay. So part B is where all the action takes place. Find the dimensions that yield a maximum area. And then be sure to show or explain how you know it is a maximum. So let's start with area. Well, we already know the area of a rectangle. The area of a rectangle, and remember this is rectangular, the area of a rectangle is length times width. So in my problem, length times width is x times y. Now, ideally, I'd love to use this formula, but I have 2 variables, x and y. I'm going to need just 1 variable if I'm going to optimize, which means I'm going to take a derivative. So we have to use what's called a constraint. What piece of information do we know that we haven't used yet? Well, let's check. If we read the 3rd sentence, we have the following. There is 18 feet of wall material for each cubicle. Now, what is that? That is a perimeter value. We are given a perimeter value. We're told that there are 18 feet of wall material. So 18 should be equal to all of the walls added together. In other words, x plus y plus x. If I add up all 3 sides, x plus y plus x, it should equal 18. Well, what does that mean? Well, that means 18 is equal to 2x plus y. And so what we can do is we can solve for one of our variables. Let's solve for y. I'll get 18 minus 2x is equal to y. So I'm going to create a single variable area equation. If the area is x times y, and I know that y is 18 minus 2x, then using distribution, my area is 18x minus 2x squared. All right, now that I have the area and I know I want to maximize the area, I'm going to take this derivative and look for a maximum. So we're going to differentiate and find a maximum value. All right, well, my derivative is 18 minus 4x. If you're looking for a max, or if you're looking for a min, you're looking for what we call an extrema. To find extrema, you look at where the derivative is undefined and where it's equal to 0. Now, our derivative is never undefined. We don't see any division, we don't see any square roots, so it's never undefined. But it could be equal to 0. So what happens if we set it equal to 0? Well, we're going to get, if we add 4x to both sides, 4x is equal to 18. And if we divide, x is equal to 18 over 4. That, of course, is going to be 9 halves. That's an ugly 9. 9 halves, which would give us, let's see, 4.5. Okay, now we have to show that this is a maximum. So I'm going to do that off to the side in green. Is x equals 4.5 a max? Well, in order to do that, we can create a number line. 4.5 is our critical number, and we know that the derivative is 0 at 4.5. So let's choose some test values. I need a number less than 4.5, I'll choose 1, and bigger than 4.5, I'll choose 5. We plug these test values into the derivative. Here's my derivative. If x is 1, I have 18 minus 4 times 1. That's something positive. If x is 5, I have 18 minus 4 times 5, which is 18 minus 20, which is going to give me something negative. So we can see that I am increasing and then decreasing. So of course, I must have a max at x equals 4.5. So we showed that we know it's a maximum, so we just need to answer the actual question now. And the actual question was to find the dimensions. Well, if x is 4.5, then y is 18 minus 2 times x, which means y is equal to 18 minus 2 times 4.5, and that'll give us 9. So our dimensions, we're going to need units. And remember, we were using feet for our units because we were told we had 18 feet of cubicle. So our dimensions are going to be 4.5 feet by 9 feet. A decent size cubicle for this company.